Assalamu alaikum wa rahmatullahi wa barakatuh. In this series of videos, we are going to talk about Chapter 9, Self-Induction, which is the second chapter of the second unit, Electricity. At the end of this chapter, we are going to be able to define the phenomena of self-induction, define the inductance of a coil, give the expression of the self-induced electromotive force, write the expression of the potential difference across a coil, read the graphs of the growth and the decay of a current in RL series circuit, establish the differential equation of the growth and the decay of the current in RL series circuit and give their solution, know the physical significance of the time constant, give the expressions of the magnetic energy stored in a coil, and interpret the spark produced when switching off a circuit. In this video, we are going to explain the first two objectives, define the phenomenon of self-induction and define the inductance of a coil. In the previous lesson, we saw how the magnetic field of a first coil affects another adjacent coil and induces a current that tries to oppose the magnetic flux change caused by the first coil. This was known as electromagnetic induction. Now, when this EMF is induced in the same circuit in which the current is changing, this effect is called self-induction, which is the subject of our lesson. To understand the phenomenon of self-induction, let's study the following experiment. The materials needed are two identical lamps, L1 and L2, rheostat, which is a resistor of adjustable resistance R, coil with an internal resistance R, and a DC generator of a constant voltage E, and a switch. Now, after closing the switch, we notice that L2 glows instantly, while L1 glows gradually with a noticeable delay with respect to that of L2. Then L1 glows as brightly as L2. Faraday's law can be used to describe this effect. As the current increases with time, the magnetic flux through the circuit loop also increases with time. This increasing flux creates an induced EMF in the circuit. The direction of the induced EMF is opposite to that of the EMF of the battery. The induced EMF causes a current which would establish a magnetic field opposing the change in the original magnetic field. So the self-induction can be defined as the phenomenon in which a change in electric current in a circuit produces an induced electromotive force in the same circuit. In the previous experiment, we saw that the current is affected by self-induction phenomenon. In order to visualize the variation of the current under self-induction phenomenon in the case of growth and decay, we will study the following experiment. We will need a square signal generator. In the case of square signal, the voltage V increases from 0 to a constant value V0 suddenly at t equals 0 and remains constant until t equal half period. Then it drops instantly to 0 and remains constant until t equal 1 period, and this process is repeated periodically. In addition to the low frequency generator, we need a resistor of resistance R equal 500 ohms, a coil with internal resistance R. We set up the circuit as shown in the figure. The coil is connected in series with the resistor, and we connect the channels of the oscilloscope in order to visualize on channel 1 the voltage UAC across the terminals of the generator, and on channel 2 the voltage UBC across the resistor. And note that the generator is delivering a square signal of value E in the first half period and 0 in the second half period. Now, as we know that the oscilloscope visualizes the voltage and not the current. So in order to visualize the current, we always connect the oscilloscope across the resistor, since according to Ohm's law, UBC, which is the voltage across the resistor, is proportional to I since U equal Ri, and R, as we know, is a positive constant, so UBC, the value of the voltage across the resistor, represents always the image of the current I. Now, when UAC, the voltage across the generator, jumps suddenly from 0 to E, the current I reaches its maximum progressively, and this is called the growth of the current. While when UAC falls suddenly from E to 0, the current decays progressively. This observation can be explained as follows. When the current flowing in the coil varies, the coil is the seat of self-induced EMF, E. According to Lenz's law, E tends to oppose the variation of this current, so it delays the growth and decay of the current. As a conclusion, the coil has the tendency to delay either the growth or the decay of the current. The phenomenon of self-induction appears only in circuits containing coils traversed by a variable current. With direct current, self-induction appears at the time of switching the circuit on or off. Now, as we saw earlier that the resistor is characterized by its resistance R, or the capacitor is characterized by its capacitance C, also the coil is characterized by a constant called inductance of a coil. In order to determine the expression of this constant, let's use the expression of the magnetic flux. In the first figure, I is directed along the same direction as that of positive sense. Due to right-hand rule, we can determine the direction of the magnetic field vector B. The normal unit vector have the same direction as that of the magnetic field vector B, so the angle between B and N is 0, so the flux will be equal to NBS, which is a positive value, like the sign of the current. So I is positive and flux is positive. In the second figure, the direction of the positive sense is chosen opposite to that of the current I. So the direction of the normal unit vector now will be opposite to that of B. So the angle between B and N will be 180 and the value of the flux will be negative. Also like the current, since the current is opposite to the positive sense. As a conclusion, the current I and flux have the same sign. As we know that the magnetic field created by a current inside the solenoid is equal to B equal mu 0 and I over L. And since flux equal to NBS, we replace the value of B and we will have flux equal N mu 0 and I over L multiplied by S, which is equal to mu 0 and square S over L multiplied by I. Since mu 0 and square S over L is a positive constant, we can deduce that flux and I are proportional. So flux and I are proportional and having same sign. Now we can say that a coil traversed by a current I has a self-flux phi such that this flux is equal to Li, where L is a positive constant. In the case of coil with no soft iron core. So flux will be equal to Li, where flux in webers, I in amperes, and L in henries. Note that the introduction of a soft iron core inside the coil increases its inductance L, and in this case L varies with the variation of the current and no longer a constant value. Now let's solve application 1. A solenoid of N turns has a length L where R is the cross-sectional radius of the coil. Determine the expression of the inductance L of the solenoid. The magnetic field vector created inside the solenoid is equal to 4 pi times 10 to the power minus 7 and I over L, and the self-flux is equal to NB dot N times S. Replacing the expression of B in the equation of phi, we get flux equal NS 4 pi times 10 power minus 7 Ni over L, and since flux equal Li, L equal to 4 pi times 10 to the power minus 7 N square S over L. Now let's remember that self-induction is defined as the phenomenon in which a change in electric current in a circuit produces an induced electromotive force in the same circuit. The coil has the tendency to delay either the growth or the decay of the current. The phenomenon of self-induction appears only in the circuits containing coils traversed by a variable current, and a coil is traversed by a current I has self-flux such that flux equal Li. This is the end of part 1. Thank you for your listening.